Okay, so thanks a lot to the organizers for this opportunity to speak. Yes, so I'm going to present some recent work with Antonio Garcia, who is a condensed matter physicist in Shanghai, and some more recent work with Antonio and some of his students in Shanghai. Okay, so yesterday some of the speakers spoke about ADSCFT. So let me just recall what is ADSCFT. So ADSCFT is a duality between quantum gravity in ADS and a conformal field theory living on its boundary. And it's an exact duality. And this duality is very interesting because the field theory gives you a non-perturbative definition of quantum gravity in ADS. And semi-classical gravity gives you a way to solve strongly coupled field theories. And in this talk, I will show you a little bit how this works in a toy model of ADSCFT called nearly ADS2 holography. So nearly ADS2 holography is a duality between the SYK model, which is a very simple quantum mechanical model, so in 0+1 dimensions, given by this interaction Hamiltonian. So as you can see, it's just a psi I here is a Majorana fermion. And we just have a 4-point interaction between these Majorana fermions. And this coupling GIJKL is going to be disorder average over. But so you see, this model is extremely simple. It's as simple as you can get for interacting quantum mechanics, right? And it's very interesting because it has a lot of features of quantum gravity. And indeed, this model was shown to be dual to JT gravity, which is a simple two-dimensional theory of hyperbolic surfaces, and a good toy model of ADS2 holography. So here, the way this was shown is just by the fact that both theories reduce at low energy to the same effective theory called the Schwarzschild quantum mechanics. And here I'm thinking of JT gravity as a kind of approximation of the exact dual of SYK in the same way you would do in higher dimensional ADSCFT when you think of ancient gravity as an approximation of string theory. And so nearly ADS2 holography, so this SYK JT duality, has been extremely successful in recent years. So I don't have time to review the many successes it had. But one general lesson I want to emphasize that we have learned from it is that non-perturbative effects can be studied in semi-classical gravity using the path integral approach by summing over geometries. So this is very surprising because you would think that semi-classical gravities, which is just an approximation of the exact theory, should not know about any non-perturbative effect. But actually, it seems that it does, even though it's not very well understood as of now. It's an active topic of research. So what is the gravity path integral? It's just the basic idea of quantum mechanics that you have to sum over all configurations. So, for example, let's see how this works for this duality. So if you compute the theory with a circle boundary, so in the quantum mechanics, it just computes the partial function, trace e to the minus beta h. And in gravity, the prescription is that you have to fill in this boundary by a space-time. So the leading contribution is going to be this disk geometry, which is actually also called the cigar, or it's a black hole, it's a Euclidean black hole. But you can also have subleading contributions, such as this higher genus one. And for two circle boundaries, for example, so in this case, you just compute the product of these two partial functions, and the leading contribution is going to be this black hole, these two black holes, and then you might have some connected contribution like this wormhole. And here I want to emphasize, I'm looking at the average theory, so that's why you have this bracket here, where you average over the SYK couplings, and this is going to be important. So for example, let me just give you an example to one of the successes of nearly ADS2 holography, and it's the spectral form factor. So this is an example where semi-classical gravity has been used to obtain detailed non-perturbative information about quantum gravity or about the statistics of black hole microstates. So in the case of SYK, you have this Hamiltonian, this strongly coupled Hamiltonian, and you can diagonalize it, find the energy eigenvalues. And these energy eigenvalues, you can think of them as the energy of the black hole microstates. And the statistics of this eigenvalue is really interesting. And you can study it by looking at this quantity, the spectral form factor, which is just obtained by taking like this quantity, the two boundary quantity with beta L and beta R, and analytically continuing in time, in real time, and then plotting this quantity as a function of time. And you see this distinctive feature where you have first a dip, and a dip which just is the consequences of the fact that this will introduce random phases. So it's going to decrease at first. And then you have this ramp, which is a consequence of the fact that these energy eigenvalues have some property called eigenvalue repulsion. So it's because they have the statistics of random matrix theory that you have this ramp. And what is rather incredible is that in semi-classical gravity, you have these two contributions, and the first contribution gives you the dip, but the first contribution would just go to 0 after that. And the ramp actually is given by the second contribution, the wormhole. So it's very interesting that just by doing this kind of very simple geometric computation in semi-classical gravity, you can get this kind of detailed information about. And here, what you get is not, you don't get this erratic behavior that corresponds to a single validation, but what you get is the average behavior. So it seems that the gravity path integral computes some kind of ensemble average. So, okay. But so this is the story of SAT Schenker Stanford. And today I want to give you I want to study what I think is a more realistic story, because this SAT Schenker Stanford story only works in pure JT gravity, which I think is a very special theory. Because for example, if you just add matter, then it doesn't work. Because if you add matter to the model, the path integral cannot be computed exactly. And you have to resort to saddle points, which is not what they did. But I think the saddle point description of the path integral is more realistic because it's what you expect in higher dimensions, for example. So here, I'm just going to add this massless scalar fields. And by adding this massless scalar field, you can get one of these wormhole solution if you add boundary sources. So you just impose, a boundary condition for the scalar field like this. And here you have to take imaginary sources. So basically, you have to analytically continue this partition function for imaginary values, and then you will have this wormhole contribution. So this is a solution we studied in this paper. And so in JT gravity, the boundary source is corresponding to adding this deformation to the Hamiltonian. So this is something that is standard in ADSCFT. It's just the ADSCFT dictionary. And in SYK, we can model this by adding an imaginary part to the coupling. And you see, because this imaginary part has exactly the same effect. And then you can just compute different observables to compare these two models. And we find an excellent match between the two. For example, the free energy here displays a first order phase transition between a wormhole phase, which is the flat phase here, and the black hole phase. Okay, maybe I'm going too slow. And we can see the same thing in SYK. So yeah, let me not spend too much time on this actually. Another thing we can do is, here we understand the wormhole as a consequence of the SYK average. So we can ask the question, but what is the dual of SYK if you don't do the average? And this is something we studied in this recent paper also. And you can understand this in terms of half wormhole. So the idea is that at a single relation of the coupling, you have this additional boundary condition, and the dual of JT is the theory where you have this half wormhole. Whereas when you do the average, so you integrate over the J, you only have the wormhole. But okay, let me not go into this too much also. And then another way to build a wormhole, which was studied by Maldacena and Chi. Oh, I think they cannot hear the say. Can you hear me?
I can hear, Victor. I can hear.
Okay. Yeah, so, okay, before going further, I want to mention another way to build a wormhole, which is instead of having these boundary sources, you can have an explicit coupling between the left and the right boundaries. So in SYK, it's given by this two fermion term, and in JT, just some explicit coupling of this type. And the solution you get is the eternal trustable wormhole, which is just the global ADS2 geometry, which has the infinite strip, this infinite strip. And so what we did in the most recent paper is to study this combined system where you have the two effects I just described. So you have these boundary sources or these complex couplings with parameter k, and also this inter-site interaction, this explicit coupling eta. So the full Hamiltonian takes this form. And we can solve the model at large n in SYK using the Schwager-Dyson equation. And in JT gravity, we have, can you move this one? In JT gravity, we have this, we also have this, and we can compute the path integral using saddle points. And here it's quite interesting. Like if you, okay, I'm not going to give the details, but there are basically three wormhole solutions given by a solution of the cubic equation. So the path integral is quite intricate, but also analytically solvable in this saddle point approximation. So let me not go into this, but let me tell you now how does these two compare. So
Victor, 4 more minutes.
Yeah. So the physical quantities here will be function of these two parameters k and eta. And in SYK, we can only solve this Schwinger-Dyson equation numerically. But in JT, we can do it analytically, and it gives a way to, it gives an analytical expression for this physical quantities. So for example, the energy gap associated with the wormhole phase has this expression, and we can compare this SYK and JT results, and we find an excellent match. So in SYK model, we can directly study the energy spectrum by just exact diagonalization of the Hamiltonian numerically. And the energy are going to be generally complex because the Hamiltonian here is non-Hermitian due to the complex couplings. So this is a system that we have to study in Euclidean signature from the point of view of statistical mechanics. But the system doesn't generally have a Lorentzian interpretation. But for eta, for this intersite coupling sufficiently large, we observe a transition to real spectrum, so a complex to real transition. And we can diagnose this transition by another parameter, which is just the derivative of the partial function with respect to this parameter k. And in SYK, this gives you the imaginary part of the Hamiltonian, so that's why it's associated to this complex to real transition. And in JT, it gives you an operator that you can show to be an other parameter for the symmetry breaking SL to R goes to U1 from the Lorentzian to Euclidean black hole. And I'm going to explain this a little bit more, but here's a comparison of these two quantities in SYK and JT, and we can see like that it's a good match. And so the idea is that this complex to real transition in SYK should be viewed as a kind of Euclidean-to-Lorentzian transition, because it corresponds to the restoration of the SL to R symmetry of the Lorentzian black hole, wormhole, broken to U1 in the Euclidean wormhole. Because the difference between these two geometries, so one of them being the analytic continuation of the other, is that this geometry has SL to R symmetry, whereas this one, because you have compactified time, only has a U1. And it's interesting that we can see this Euclidean-to-Lorentzian transition as a dynamical restoration of this SL to R symmetry. And interestingly, this involves a change of integration contour in the gravity path integrals. So this is something that this choice of contour is not very well understood. And I think this model gives a nice example where we have a microscopic SYK dual that tells us what should be the right contour. Another thing that we can compare is this phase shift in the green functions, which is sensitive to this transition. And I mean, this is just to show you that there is a detailed match of all possible physical quantities that should be in this regime where the duality is valid. Okay, and so let me conclude now. So we have studied JT gravity with massless scalar and its dual SYK model. So this gives a simple toy model where many non-perturbative effects in quantum gravity can be studied, such as this thermal phase transition between a wormhole and two black holes, so a type of Hawking phase transition. The average and factorization using half wormholes, so the question of what is the dual of a single relation of SYK. And this gravitational symmetry breaking interpreted as a Euclidean-to-Lorentzian transition. And I think there are also many more possibilities offered by this model, which will be studied in the future. And also another thing that would be interesting to do is, I think, to generalize these results to higher dimensional ADSCFT which appear to be possible because none of this value, we didn't use the fact that we are in 2 dimensions in most of the analysis. So thanks a lot for your attention.
Thank you, Victor. We can go for questions now. No time for 2 questions, maybe 2-3 questions.
So you have mentioned that JT Gravity and SYK is dual to each other. So you have mentioned 2 possibilities that the coupling of SYK, like JIJK, is one case it's averaged, another case it's not averaged. So both the cases it is dual to JT Gravity?
Yes, so the point is that for many quantities, actually, they are self-averaging. So it doesn't really matter if you look at, the theory as a single realization or the average theories. So for example, for most of the black hole observables, they are going to be self-averaging. But here we're talking about some observables that might not be. So for example, the free energy with 1 boundary, actually, oh, this is the slide that is missing here. The free energy at 1 boundaries is going to be very sensitive to the choice of coupling. And this is why this duality is interesting, because the proposed duality here is that it's dual to this half-formal solution where you fix this boundary condition J. And this J is what is dual to the JIJK in SYK. And you can also show that the free energy, including this solution, will have the same kind of very sensitive dependence on this function J as SYK has in the function.
But what happens to this spectral form factor? In both the cases, it behaves like same way?
No, so the spectral form factor is not something we study. So,
but I'm just asking that what happens.
I just mentioned it because this was one of the first example of this kind of ideas. And here, actually, we cannot really study the spectral form factor in our case because we are talking about a non-Hermitian Hamiltonian. So the system is a bit different. So here, this is just SYK, the SYK model without anything else. Whereas in our case, we add a little bit. So we look at these boundary sources, and we also add this interaction. And in these cases, the spectral form factor is not really a good quantity.
Okay.
So even in the eternal traversable wormhole, for example, the spectral form factor is not really a good quantity.
But how you decide that? Whether it is a good quantity?
No, I mean, we could compute it, but it's just not interesting.
Okay.
Hello. Yeah. So can you explain a bit more about this non-Hermitian nature? Where does the non-Hermitian nature came from? I'm kind of.
Yeah, so it simply comes because, so here, yeah, because our goal was to find a wormhole solution of this type.
Okay.
But this is not that easy to find because if you just impose these boundary sources, actually the solution doesn't work in general. But basically because you need some kind of negative energy to stabilize the solution. And that's why real boundary sources are not going to do the job. You need to analytically continue to imaginary boundary sources. And so in the SYK dual, it corresponds to adding this imaginary part to the coupling. And at the end, what you get is a non-Hermitian Hamiltonian. So you get a Hamiltonian with complex and eigenvalues. And this Hamiltonian, of course, there are many ways you can interpret it, but we want to just view it from the point of view of statistical mechanics. So basically, we just compute trace of e to the minus beta h and study this quantity. But I think there might be other ways to interpret it, perhaps as some kind of dissipative system. I mean, we have thought a bit about it, but we haven't. We haven't made this precise.
So the statement is that you just on the SYK side, you just add some imaginary couplings and
exactly. And because this is something relatively easy to analyze using, let's say, Schwinger-Dyson equation, and this is why, like you can see, if you look at what this adds, it basically just adds I times k times some marginal operator, because this 4 Fermion term is a marginal operator, which is exactly what we are doing in JT. So that's why this duality works.
Okay, and so am I right in saying that the partition function is also then not real?
is also?
Not real.
Yeah, so the partition function, if you only have one of these boundaries, it will be complex. But because we have these two boundaries that are complex conjugate to each other, the partition function is real at the end.
Okay. And okay. Fine.
Yeah. Okay. Thanks for the question and talk.